Hello, everyone. Before this lecture begins, I want everybody to know right away that this is a very particular lecture to people who want to understand the notion of a coordinate basis. It's a long lecture that just goes through every element of this story from beginning to end, redundantly, pedantically, carefully, and I hope with some degree of clarity, although everybody's vision of clarity and it's all different. I'm really trying to walk this through from the beginning to the end. My previous lecture on this was in the What is a Manifold series. I don't think it went over that well, so this is an attempt to redo it. But this is a very long lecture, and don't get started with this lecture if you're comfortable with the coordinate basis already. If you're not, then go ahead and put this at 1.5 speed and listen through it and slow it down at the parts that are hard. But it's one really long lecture, and if you need it, and I hope it helps, let me know in the comments below. And if not, I'll try again, because this is such an important point, and I'm very aware that students are struggling with it. Okay, good luck. All right, I want to do a lecture going back and talking about a really, really important subject, coordinate basis. And I didn't probably appreciate how difficult this subject was. For some reason, I understood it when I was learning it pretty naturally. And what I probably mean by that is I didn't fully understand it, but thought I did, so I never had a problem with it. And then by the time I realized I didn't fully understand it, I had all the tools to learn it. So I never struggled with the idea of the coordinate basis. However, I've been noticing that many people do, and in fact, it's a huge sticking point. And by the coordinate basis, I'm talking about this basis, the basis where we use partial derivatives as though they are basis vectors of the tangent space at a point P of a manifold M. And its corresponding relative in the dual space, which I guess we sometimes write as either T star P of M, or so if we call this the vector space, we would call this the dual vector space. I should make sure. Dual vector space, by that I mean V, and I usually put an asterisk. So I want to dig into this concept one more time. I've covered it in the What is a Manifold lecture, and I'm going to basically do the same proof but more carefully. And I'm going to substitute this lecture into, or substitute it, I don't know. I'm going to insert it in both playlists, the GR playlist and the Manifold playlist, which go together, right? The Manifold playlist is a great thing to have done before the GR playlist. In fact, it's almost mandatory. I should have just bound it all together in one gigantic playlist of hundreds of videos, I suppose. Okay, so let's talk about this. Let's get it down. If you are ever looking at these coordinate basis vectors and wondering what the heck is going on with these differential operators being basis vectors, well, this is my best shot at explaining it. It's not easy. It's very systematic. It takes a while. But at the end, it ties together, and it is what it is. So let's begin. So we're going to begin this construction with the typical starting place, a manifold named M. And the manifold M will have dimensionality, a fixed dimensionality. We'll say it's a value of dimension M. In general relativity, of course, this will be 4, but it could be anything because we're being very abstract. So now when I say we have a manifold M, what immediately has to pop into your mind? Immediately, you have to be thinking, oh, well, it must have a coordinate system, because any manifold, by its very definition, has to have a coordinate system. So we immediately start thinking this picture should pop into your head every time you think of a manifold M. You imagine a representative point, which we could call P, and around that representative point, you have a chart region, which you might call U, and that chart region has a mapping into R dimension M, right? So if the dimension of M, let's just simplify that. Let's call that little n. So this maps into Rn, where n is the dimensionality of the manifold. And you know that this is, just to be really clear, I don't know who's approaching this video from what level, But this fact, the fact that you can create this chart around every single point in M, every point in M will have some, chart. You'll be able to define a chart U around it, and that mapping from that chart into Rn is a diffeomorphism. Well, let's call it a homomorphism. It's a not a homomorphism, a homeomorphism, right? Meaning it's one-to-one, it's onto, it's invertible, it's all these beautiful properties that every good, nice mapping should have. That is the coordinate system, right? That is the coordinate system. And this exists, as soon as you say it's a manifold, all of this exists for every single point in the manifold, right? Now we're talking about general relativity, of course, so this manifold is our model of space-time, and this Rn, which is, some Euclidean space, that is the coordinate system that will label every single point P. Every single point of the manifold will be mappable into Rn, and the value of each of the coordinates in Rm is the coordinates of P. That's the definition of this. So these chart mappings I typically would call gamma, but you have to specify it for which chart, right? So gamma of U, for example, would be the chart mapping for U. And then there's other issues, right? There's other things like clearly, point P will have other charts that can surround it, V, and then there's the two charts will have an intersection, and V will have its own mapping into its own Rn, right? Rn. And that mapping will be gamma V. And then this mapping from Rn to Rn would be, basically it would be gamma V inverse after, it would be gamma U after gamma V inverse. That would go here and then here, and that's equivalent to this. So this mapping here is gamma U after gamma V inverse. And all of these are continuous differentiable functions in terms of the coordinates in Rn and Rm. So this is, what I just said was very quick, right? But whenever I say manifold, that's what you have to think. You have to be that good with this now. When you see the word manifold, you should immediately think, all of the stuff I said should flash through your head. And it's sort of a lot to keep track of, but if you can't do it, then you don't really know the definition of a manifold. You have to track the definition of a manifold to use the concept. Okay, so we start with this. Our space-time is a manifold. It's in general relativity, it's a four-dimensional manifold, and that is by assumption. That's an assumption of the theory. It's just like we say space has three dimensions. That is at some level an assumption, right? We only see three, so it seems reasonable. Well, at some point, through special relativity, we realize, there's actually four meaningful dimensions in the way we understand the nature of how to label places in the universe. And so our assumption for general relativity is that the dimensionality of the manifold is 4, and every point in space and time can be assigned a spot in that manifold. And because it's a manifold, every point in space and time can be given coordinates. Now, the next thing we usually do is, in order to simplify this picture, what we usually do is we actually kind of just draw the coordinate lines directly on the set that we're calling the manifold, right? So we would draw, say, some coordinate lines like this, and what we're doing here is we're really taking this mapping from these charts and we're kind of just throwing it all into the manifold just to say, okay, it's a manifold, so we can so every point, we know every single point has coordinates, so why don't I just draw it right on that set? But what I'm really doing is I'm taking each point and mapping it into Rn and taking those numbers and calling it the coordinates. Now, this gamma is actually, so you could write this as gamma of the point P, and that is a point in Rn. So gamma of point P, to be a point in Rn, means that you are a list of coordinates. You are x0, x1, x2, ... xn, right? Or I guess xn minus 1, if you start at 0. So so there's actually n coordinate functions, right? I could say x0 of p, and that's the x0th coordinate of the point P. I could say x1 of p, and that's the first coordinate of point P. So if I'm going to label my coordinates as xi, I can call gamma just x of p, and that's a perfectly fine way of doing it. In fact, it's the way we're going to do it for this lecture. X of p is the coordinates of the point P, and what that really means is it's this mapping right here. So this is where we start with our space-time, right? And our goal is to understand how to do these this coordinate basis. So the first thing to understand the coordinate basis is to understand the coordinates. What coordinates are we talking about? And we're talking about the coordinates that are assigned to the labeling the points on a manifold. And that manifold models space-time. So we have our space-time, we model it with a manifold, every point in the manifold has coordinates. That is the coordinate system. Now, I'm not going to bother with the issue of it's only good on one chart, right? You can't find a chart for the entire manifold. You need multiple charts to get coordinates for the whole manifold. No one coordinate system can cover the entire manifold, usually. I mean, simple manifolds, yeah, you only need one chart. But almost every relevant story of space-time, especially black holes, you can't do it that way. You need multiple charts. Even as something as simple as a sphere, you need two charts, at least, to cover unambiguously every point. We're just going to not worry about that right now because it's not as important. We're just going to work within the region of one chart. And so I'm not even going to bother to draw that chart. I'm just going to put all the coordinates on the manifold. Whoops, let me erase. So I'm going to erase the chart. And we'll, as soon as you see the fact that we are dealing with a coordinate function, you know that we're talking about a coordinate function on some chart, because that's the way manifolds are defined. They're defined as that you have charts, and each chart has a chart mapping, right? And in fact, sometimes this whole thing is called a chart, right? It's a subset with a map, right? And you call that whole thing a chart. Fine. Sometimes you call this the chart and this the chart mapping. None of that is, it's all totally semantic, right? So, when we talk about our coordinate basis, when I say coordinate, I am always referencing the coordinate system of the space-time on the manifold. That's the absolute first thing you have to understand. Okay, so now that we've established that our manifold is our model of our space-time, what problem are we trying to solve? Let's talk about that. All right, so now that we've kind of covered what the manifold was and what your head should be about the manifold, I'm going to now just drop it in there. We're going to call the manifold M, and I've already short-circuited everything. I have some points in the manifold. That one's P, that one's Q. These black spots are points. I've drawn a coordinate system on the manifold, which is a shorthand for all of those chart maps, and we're ready to go. Now, previous lectures about this, what I said and the way I described it is I said at the point P we erect a vector space, right? And we call that vector space TP of M, the tangent space at the point P of M. And at the point Q we erect a vector space called the tangent space at the point Q of M. And that's fine, except that the language when I say we do something, in this case we erect a vector space, it implies that I have a manifold and I've decided to create a vector space at every point. And the problem is I decided. When I say I decided, or we erect, right? That is a statement that we as mathematicians or as physicists modeling space-time, we are creating a mathematical structure at each point. And we're doing that of our own volition in the sense that if we didn't do it, it wouldn't happen. I know this sounds kind of strangely philosophical, but think about it this way. The manifold, I have already said, is our model for space-time, right? That is a decision that we made as physicists and mathematicians. That is a foundational idea that we can only explain because we're giving it a try. We're creating a model. We have to use mathematical objects, so we've decided a manifold will be the mathematical object for space-time.
In fact, we go further. We say it's, as if we're physicists doing this, we say it's a four-dimensional manifold, and we imply that it's all locally Lorentzian and some other facts. So these are things we assert. So when I say we erect a tangent space at each point, and I think I've used that language a lot, which is unfortunate now because we don't erect a vector space in space-time. We don't erect these vector spaces. They are there automatically. Once we have a manifold by its very nature has a coordinate system, as we've already talked about, but by its very nature, it has these vector spaces at every point in space-time. You can't have a manifold without tangent spaces. And so this isn't a step that we take. This isn't part of the constructed architecture of space-time. Once we've established the manifold, it comes with these things, right? And that fact might be one of the reasons why understanding coordinate basis is so difficult. Is I want to now explain why it is that these tangent spaces automatically exist. All right? So let's begin that. All right, so let's now go back to our manifold M. You've put in your mind all of those things about coordinates and mappings I've told you about. And for example, we have the mapping, basically X. Our coordinate system will be called X, so we're going to call the chart mapping from the manifold to Rn, we're going to just call it X. And now we can think about a function on this manifold, right? So let's start with a function on the manifold M. So the function is a function of points on the manifold. So if I have a point P, then in principle, if I take f of P, I end up with something that lies on the real line, right? So it's a real function of the point P, or of the points on the manifold. I don't know why my line's so curved. Let me redo it there. Okay, so there we have it. So we have point P in the manifold, a function f from the manifold to the real numbers in f of P. This is not related to the chart mapping. The chart mapping takes the point P and returns the coordinates of the point P, right? So the idea is that any point on the manifold will be graphed to values on the real line. And so what we can consider for this particular function is we can look for all the points in the manifold, for example, that have the same value for R, right? So all the points where if I go back into the manifold, I end up with the same value. So this would be point P, point Q, point R, point S. So this is f of P, this is also f of Q, it's also f of R, it's also f of S. All those points are right there. It's the same value. And certainly there's going to be some, what's the word? Some, I think the word is locus. Some locus of points that are all going to share the value R. And I'm connecting them all with that black line. So all the points in M on that black line have the same value of R. And that's, of course, it's a contour line, but it's called a level set, right? It's called a level set. And presumably, these level sets exist all over. They all just have different values. So I can have a different level set there, a different level set there, and each of those level sets goes to a different value of R. But all the points on those level sets share the same value of R, right? And, there's a single point in the middle that is its own level set, and it's like the maximum value of the function f, or the minimum value of the function f on the manifold. So this is one way of understanding a function on the manifold, is you look at all of its level sets, and that gives you some kind of intuitive picture of how that function behaves. All these functions are smooth, by the way. All these functions are differentiable and smooth. So what do we mean by f is differentiable, right? Because this manifold M is just some random set, right? When I say f is a differentiable function, what the heck am I talking about? F is, the way I've drawn it, it's a mapping from M to R. So I have to take the derivative with respect to points in M, right? So that doesn't make any sense. So this is all shorthand. When I say f is differentiable, what I really have to mean, right, is f, when I talk about f as a function from the manifold, sure, but a manifold is so tightly bound to its coordinate system that what I really mean is it's a function from Rn to R, because it's a function of the coordinates. So what I want it to be is really a function of from Rn to R. And now I can take derivatives. I can take partial derivatives, right? It's multivariable calculus at this point. I can take partial derivatives with respect to each of the coordinates which actually live in Rn. So what I'm really talking about is actually it's actually, the way I've defined it, it's actually f after x inverse, right? That's the function that maps from Rn to R. And again, once we talk about manifolds, we tend not to think too much about the inverse chart mapping, right? But if I define f as literally from the manifold to R, then if I want to use the coordinates of these points, I'm really having to use the coordinates in Rn. So I have to map the point into Rn. But likewise, if I want to use the coordinates to sort of get at the function f, I have to start at the coordinate point, map it back here, and then bring f onto the real line. So the function that goes from Rn to R, all right, that function is actually f after x inverse, right? That's the name of the function that graphs from Rn to R. And that function is differentiable. And that's what we mean by a differentiable function from the manifold, is we're talking about the differentiability of this guy. All right, now with that notion of a function in hand, we are facing one of these little philosophical points that will get us to where we need to be, that we got to wrestle with. One is, if I talk about a specific function f, then that demands a lot. It demands I choose, first of all, a specific manifold, but we're allowed to choose a specific manifold. So we imagine that of all the manifolds that are possible in the mathematical universe, that in the mind of the physicist or the mathematician who's doing this, we have picked one, right? Now, on that one manifold, there are many, many, many possible functions that will produce, that will operate on the points of the manifold, or operate on the coordinates of the point of the manifold, as I just kind of went through in painful detail when I described this guy right here, when I described f after x inverse. So picking one function is an act of decision-making on the part of the mathematician, right? If we picked one function for this story, we are adding something that we didn't have before into the problem. We are specifying something, right? We've specified the manifold and we're happy with that, but we now have to consider specifying a specific function, right? Well, how do we do that? Well, the way we do that is we go to the set of all possible functions, f, g, h, r. All of these functions are functions on the manifold that behave exactly this way, but they're all different. And this is a set of every possible one. And I will call that set C infinity M. I think that's pretty typical. The infinity means infinitely differentiable, right, in the sense that of multivariable calculus, right? The differentiation of this guy here. So this set of all the differentiable functions, I have to go in and I have to pick one. I have to pick one out and pull one out. Pull out G, maybe I pull out H, right? I've already kind of talked about F, right? So this act of pulling one out, right, that is a specific action taken by the mathematician. But notice the following point. The set that the mathematician used to dip into, to pull out a specific function. That set, C infinity M, that set existed whether the mathematician pulled something out of it or not, right? That set I offer to you. And when I say I offer to you, what I mean is this is the way I think about it, right? This is my point of view, right? This set exists. As soon as you have a manifold, right, the set of all possible functions from that manifold to the real line, that exists. It's your choice as a mathematician whether to go in and pull out one particular function from that set. But the set of all these points exists. And what I'm trying to get you, the student of this lecture, to appreciate is that a lot of things appear when you choose a manifold. And one of the things that appear is the set of all possible functions from that manifold to R. That exists automatically, right? It exists automatically. And so, so we didn't create this set. We did nothing. We added nothing because it's a set of all possibilities. So with the set of all possibilities, it doesn't get constrained in any way by any action or thought or decision that we're making. So this guy exists, right? Exists, right? That's the way I want you to think about this. That guy exists. Okay, so now with that in mind, we've got our head around this thing and what each member of this thing means. This story here, representative on F, is what is true for every single member of this infinite, uncountably infinite set. Okay, so with that in mind, we understand F. Now we're going to understand another kind of function that automatically will exist in the same vein as this, another set of functions, curves. And what I'm going to do is I'm going to show you what a basic curve is, and then I'm going to show you that there's a set of all possible curves. All right, so let's do that now. All right, so now we need to talk about curves. Again, another thing that needs to be hopefully a review in large part. But we start with our manifold, snapshot to all of the things that a manifold means. Notice I'm not including the coordinate space quite yet. Now I introduce a real number line, not as a range like we did here, right? Where here this was the range of a function f. Now I'm going to introduce the real number line as a domain. And the value along this real number line will be tau. And then I propose a mapping from the real number line into the manifold, right? This only has one dimension, right? This is a one-dimensional thing. And I'm going to call that mapping alpha. And alpha goes from the real number line into the manifold. And so this point here is alpha of, say, let's just say 0. So tau equals 0 right here. Tau equals 0. And then, as tau moves up and down the number line, this is going to trace out a variety of points in the manifold, right? And those points will also have a locus, and that locus is the curve alpha of tau, And so notice that this alpha of tau is a curve in the manifold. And because it's a manifold, that curve can be described in terms of its coordinate points, right? I can now map from that curve, right? I can map using the coordinate functions x onto Rn, right? So now this curve is actually a curve, I'll do it in red, in Rn, and every point on that curve is defined by its coordinates x0, x1, all the way up to xn minus 1, right? So I can now create a function that goes from R right into the coordinate space, and that is going to be called x after alpha, right? And x after alpha is a function of tau, which is a function. This is the domain of this. The domain of the functions and real numbers. The range is Rn. So I should write x after alpha is a map from R to Rn, right? Map from the real numbers to Rn. So now that is a curve in M. This is what a curve in the set M is. Now, there's obviously a lot of possible curves in M. Just like there were, there's an infinite number of functions that you can define from the manifold to the real line. There's a lot of curves you can define in M. They're all arbitrary. I could just sit there drawing them all day long. You can draw curves, pick a point, draw a curve through it. Pick a point, draw a curve through it. Or, more importantly, and the way we're going to do it is I pick a point and I draw many curves through it. There's one, that's called alpha. Then I might have another, and I call that gamma. Then I might have another, and I call that beta. And, there's an infinite number of curves, right? Here's a curve, ooh, and it goes through alpha, right? Every one of these things are curves that go through alpha. And it certainly is not inconceivable to think of the set of all curves that go through the point, this point P, right? A set of all curves that go through the point P. Every conceivable curve, an uncountable infinite number of curves. Notice, for example, that even this one curve that I've drawn, I've parameterized it by tau. But if I'm considering this set of all possible curves, there's another number line out there with lambda. And lambda, I'll call that curve beta. Lambda maps to here. And that might even be that lambda 0 is equal to p. P is the point lambda 0 is equal to p. But it could be that it traces the exact same curve. It just traces it faster. It could be that lambda equals 2 tau, right? So it traces the same curve, but quicker. That's a different curve. That's considered a different curve, right? And every one of these curves has an associated version that goes from the coordinates of the manifold onto the line. This piece here is so tightly bound together that we generally don't even write it. I could easily just say, look, from now on we assume that everything's done with coordinates, and you know that all of these lines are functions of the coordinates of the manifold. In this case, the range, this function alpha of t gives you n numbers representing the coordinates of the point in M. You don't even think about landing in M and then converting to coordinates. You just say landing in M and you assume coordinates at the same time, right? But these curves are how we are going to define our coordinate basis. These curves are really important. You can take derivatives of these curves with respect to tau, right? These curves are functions of one variable, tau. You can always take derivatives of these curves with respect to the parameter, in this case tau, in this case lambda. You can take the derivative of this function with respect to tau, and it'll make perfect sense. It'll make perfect sense because it's a function of tau, so you can take its derivative. Now, it turns out that this guy is actually, when I write it down this way, I guess that's a fair point to make. If I write, let's see, I was doing it in red. If I write x after alpha, we really need to remember that this is actually a combination of things. It's actually x0 after alpha, x1 after alpha, ... right? So this is a stand-in for all of these at the same time. This gives you a point x0, x1, ... to xn minus 1, because the manifold is a n-dimensional space. So each place you land in the manifold has to have n separate coordinates. So these are n different coordinate functions.
So when I say you take the derivative of this guy with respect to tau, because it is a function of tau, I'm really saying you're taking the derivative of this guy with respect to tau. Each of these independently is a map from R to R, right? Because that is a single real number, one coordinate. That is a single real number. When I think of it this way, it's a map from R to Rn. But each individual coordinate function is just a map from R to R. And that is what we're taking the derivative of. When I say we take the derivative with respect to tau, or with respect to the curve's parameter, which in this case is tau, I'm really talking about taking the derivative of each independent coordinate function. But if you think of them in combination, you can consider taking the derivative of this thing with respect to tau, as long as you understand you're going to be taking n different derivatives. And they're total derivatives. These are n different, not total derivatives. What's the opposite of a partial derivative? An ordinary derivative. You're taking all ordinary derivatives. Each of these is R to R, so the derivative with respect to the dependent variable, or the independent variable, is going to be an ordinary derivative. Okay, unlike this case here, where when we talk about taking the derivatives here, we are in fact taking the partial derivatives, which are ultimately these guys, right? Okay, so I think now our basic definitions are ready. We understand a curve, how to define a curve, and we understand what we mean by a function on a manifold. We understand how these maps are arranged, that this guy is a function of coordinates. We're trying to get from Rn to R in the case of the function, and in the case of the curve, we're trying to get from R to Rn, and that's what this guy is. We've discussed all that. Now we're ready to start putting these things together to sort of understand how we can take derivatives of functions on the manifold with respect to curves on the manifold. And obviously we're going to be talking about, if you're moving along a curve in a manifold, you're going to be crossing these level set lines, and the speed at which those level set values are changing is a way of understanding the derivative of this curve, or the derivative of that function with respect to a certain traversal, right? And that's what we'll talk about next. Okay, so before we integrate these ideas, where do we stand? Well, we stand with our manifold, right? And we have yet to define what these guys are, so I'll erase them. We don't really stand with them yet, right? We haven't erected a vector space, because I'm going to show you that is incorrect language that I've used probably too much. I guess incorrect is a little unfair, right? I'm trying to approach it from a different angle, where we don't literally erect the vector space, but you understand that it erects itself. But now that we've got this manifold, now you should also understand that automatically we've got C infinity on M. That's our set of all functions. And we need like a set to describe all possible curves, right? Let me think. What I want is some kind of word that describes every possible curve you could have on M. Like, for example, this curve here, and this curve here, and this curve here, and all the curves that go through all the different points. I mean, any conceivable curve. This is standard, right? This is notation you'll see in many, many, many books. It's not 100% standard, but it's pretty common, or some version of it. For every possible curve, how about if I write capital A on M? That's the set of all possible curves on M, right? All of these things. And the point being, though, is once I said M exists, now we know that these two things automatically exist, because we're not picking anything out, right? Manifolds, by their very nature, involve the real numbers, right? You can't define a manifold if you don't have a concept of the real numbers. You have to have a concept of n-dimensional Euclidean space. That has to exist, and chart maps and all that stuff exists. And to create these sets of complete functions, you need real numbers, you need n-dimensional Euclidean spaces. Those exist, ergo these automatically exist. So all of this stuff
comes the moment you create the manifold. I don't know. Obviously I'm sort of repeating myself here, but understanding this, that there's no understanding that this is all organic to the manifold is probably, I think, the biggest hurdle to understanding coordinate basis. Well, it's one hurdle. It's certainly an important hurdle. So now let's start connecting these two like I said I was going to. All right, so now we are able to begin with a manifold M and the level sets of some arbitrary function f identified. Right? So it doesn't matter what function we pick, it's just a member of the definitely existing set C infinity on M. Right? So an arbitrary member. So everything is still completely general. And now these level sets, of course, if I take these points P, the value of f along this particular level set might equal A. In fact, I'm going to do that in blue. So when I write f equals A like this, what I mean is along this level set, I'm labeling all the points in that level set by the value of f of every one of those points. Right? So likewise here I would write f equals B and f equals C. And every level set, I guess, here I would write f equals D, right? So all these level sets are definitely identified and established. And this idea would work for any manifold. Now we will consider a curve, right? So let's consider one particular curve. We'll call that curve alpha. And that curve, alpha, is actually going to be designed to go right along one of these level sets, in particular this one. It's going to follow this level set, right? So I'm going to call that curve alpha of tau. And alpha of tau, of all the curves that go through, let me go ahead and pick a point P here, right? There's a point P. Of all the curves that go through the point P, alpha of tau is a curve that goes through the point P and is along this level set. So note how we did this, right? Alpha came from the set, let me do it over here. Alpha came from the set A that we've talked about before. Oops. I want to do that in green. Why not? A on M. So this set exists. This set exists. We're picking an arbitrary function f, and then after we pick an arbitrary function f, we pick this alpha that follows one of these level sets. The point is that, again, we're still not making any choices because we know this set exists, so we know we can dip into it, and we also know that this curve will exist. We don't have to select it. We just know it's going to exist because this is the set of all possible curves. So this arrangement is always possible. It always and automatically exists. And likewise, I could pick beta that follows this level set and gamma that follows this level set. So given that, I can now talk about the obvious question about the composition function. And that composition function would be f after alpha. And that would be a function of tau. And another way to write this is f of alpha of tau. And another way to write this would be to say f, which is sort of a function of tau, but remember, literally speaking, or correctly speaking, not literally, but correctly speaking, f is a function on the manifold. So this is not a point on the manifold. Tau is a point on the real line. So f of tau doesn't make sense as written. But what does make sense is f of alpha of tau, because alpha is a function from the real line to the manifold, and f is a function from the manifold back to the real line. So you should be able to think of f now as a function of tau in this notation, but without that alpha, it doesn't make sense. But I could say name a new function called f of alpha, where I put the alpha down there. And that's just another way of writing that, f after alpha. So this guy is a function from the real line to the real line. So is this guy, right? These are all the same. So, it's kind of absurd that I'm writing it this way. This is a function from the real line to the real line.
So I've now created, now notice how this worked. This definitely existed, as I've said over and over again. This definitely exists. So strangely enough, these guys must definitely exist. So there's like some other set, B on the manifold, which is a set from all the real line of all possible curves to the real line, right? That automatically exists. These guys have to exist, right? And now we're getting a little far afield, but the fact is nothing here is invented or new. It's all necessary. I guess that's the best mathematical word, right? It is necessary that this stuff exists. If the manifold exists, it is necessary that these things exist. And also, this is a nice chance, because a lot of people from time to time, for some reason, I'm not quite sure why, they ask me about the axiom of choice, right? The axiom of choice, which really does not have a meaningful role here, except to say that there's no way to dip into this function, to this set of functions on this uncountably infinite set of functions. There's no way to prescribe a method of selecting one function from that set, one single function from that set. Well, I guess that's a little unfair. What I mean is, if I have if I had a bunch of sets, if I had, say, C infinity on the manifold M, and then I had C infinity on the manifold N, and then I had C infinity on the manifold Q, and I had an infinite number of these, there's really no way to prescribe a rule that picks one function from each of these sets, right? Which is kind of what we're talking about. We're talking about picking an arbitrary function. But this is saying I can pick any function from this. That's okay. You're allowed to say I can pick any function. But if you had an infinite number of these sets, and there's an infinite number of manifolds out there, so this isn't too hard to imagine, picking one function from each actually has some fundamental philosophical problems, because you can't prescribe a method for doing it, right? You can't prescribe a systematic way of doing that. So you have to assume that doing it is possible. It sure seems like it should be possible. I just pick one, pick one, pick one. But if I can't prescribe a method for doing it, it's arguable that you're allowed to do it. So the axiom of choice says, yeah, you can do it. That's a very sloppy way of explaining the axiom of choice. But the point is when we start talking about dipping into uncountably infinite sets and pulling out functions that must necessarily exist, you're kind of in that philosophical territory of, okay, can you do it? How do you do it? I don't think the axiom of choice actually is implied in any of this that we're doing, but dipping into infinite sets that necessarily exist, that sort of is in that zone. Okay, so enough about that. But anyway, the point is I want to make sure we all understand that we have this curve that follows this level set. So now, given this function, I'll look at this one, right? Because it's nice and easy to see tau is the variable there. So let's look at this notation. You can actually say, wait a minute, this is a function from the real numbers to the real numbers. And it's the independent variable, tau, is a real number. So it makes perfect sense to ask about the derivative of f of alpha of tau with respect to tau. That's an ordinary derivative. That will have a value, right? Because this guy is a function from R to R. It's some definable function. If I know f and if I know alpha, I know what this function is. And because of that, I can take this derivative. Now, be very aware, and I'm kind of going through this in excruciatingly crazy detail, but remember, when we talk about f, what we're really talking about is this function here, f after x inverse, where x is that chart mapping that goes from the manifold to Rn, right? This is what we're calling x of p. So f after x inverse is a function of of um, of the coordinates in Rn, right? So it's actually a function of x of p, right? So remember, x of p takes a point in the manifold, gives you coordinates, right? So if I start with a point in the manifold, which is p, right? I'm starting with a point p in the manifold. I map it to Rn and I get its coordinates. Now I have coordinates and I invert those coordinates, go back to the manifold, and then take the function, which ultimately lands in R. So this is a mapping. Let me just move it a little bit down here. This is a mapping ultimately from Rn to R, right? That's what F real. So when I write F, I'm really talking about this entire process, right? And that's why, and I want to introduce that because these x inverses and x's are going to be important later on. But F is sort of a shorthand because we always want to deal with the coordinates of the points, right? So when I talk about F on the manifold, strictly speaking, F is from the manifold M to R. But very frequently we will dip into the coordinate version of it, which is this, right? So just keep that in mind, right? That's kind of the facile thinking that this is the kind of stuff that makes people very confused and makes this subject quite difficult. Is sometimes we talk about F as though it's a function of the coordinates. And of course we can't, because the manifold is so strongly bound to this coordinate that this statement always exists. It's always true. It's always possible to do. So sometimes we just talk about F as though F is a function of F0, x1, x2, dot, 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 xn minus 1. But the truth is, F is actually, I need room here. F is actually a function of a point on the manifold, right? So F is really, if I was going to try to do this, I would have to say F is actually x inverse of, then I would need x0, x1, x2, dot, 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 right? So the x inverse takes me back to P, and then F takes P to R, right? So all of this stuff is in play, and it's usually contextual. I'll try to call it right out, but it's usually quite contextual. Okay, the point being, though, is ultimately this is what we're after, right? We want to study and understand this. The derivative of a function along a curve, and the curve's parameter is tau, which is a real number. The derivative of that function with respect to tau, it's a totally ordinary calculus derivative back to, your senior year in high school or first year of college, depending on the quality of your school system. Oh, and I guess before somebody asks, because it's kind of obvious to ask, this function here that I've just written, that can be written as f after x inverse after x of the point P on the manifold, right? That can be written, it can definitely be written like this. The reason we want to write it like this, f after x inverse, which is a function acting on x of P, is because we want to show this guy is a function of the coordinates, right? But both of these are the same. Okay, but getting back to this derivative, for this particular alpha, it's pretty clear that that derivative is going to be 0. The directional derivative along one of these, along a curve that happens to be sitting on a contour line of the manifold, or a contour line of the function. Manifolds don't have contour lines. Functions on manifolds have level sets, which I'm calling contour lines. this derivative is going to be 0, right? The function does not change on its value along this curve alpha. Of course, if I took a different curve, say I took the curve beta, which say might go like this. Oops, you know what? I'm not going to draw it there. I want to draw it here. Say I took the curve beta, that also goes through the point P. That curve, if I call it beta, now I'm dealing with f of beta, right? F of beta of, well, beta will have a different parameter, right? So we'll call f of beta of lambda. Lambda is now the real number parameter of this function f of beta, which is also f after beta, right? And that curve will, in fact, have a derivative, right? The derivative of f of beta of lambda with respect to lambda will, in fact, have a value, and it'll have a value at p. And I can take this derivative and evaluate it at the point P, right? And that will be a number. Now, when I say evaluate it at the point P, let's make sure we understand that, right? F of beta at lambda, because lambda is the dependent variable, not P, right? When I say evaluate it at the point P, what I'm talking about is evaluating it at, well, this is beta, first of all, not B, beta, right? I'm evaluating at the value of lambda equals beta inverse of P, right? So beta is a mapping from the real numbers to the manifold, so beta inverse is a mapping from the manifold to the real numbers. Notice that beta inverse is only defined for points that are on beta. It's not defined out here, and it's not defined out here. So it's not injective, right? Well, wait a minute. It's beta, yeah. So it's not injective from the manifold, right? It's only on this line. So beta inverse of P is a real number. And you take that real number and evaluate this derivative. You evaluate the derivative, and then you calculate the value of the derivative. Evaluating the derivative is finding a new function, right? You could call that function f of beta prime, right? And so you find that new function, and then you evaluate that new function at lambda, the appropriate lambda, such that the curve beta is at P, right? So that's what we're doing here. And it's a number. The point is this whole thing is a number. It's a real number. And with that, we begin to see what the problem is. And I hesitate to use the word problem because it's really what the richness is, what the beauty is, right? You know, what might be if your desire is to find the derivative of a function f at a point in the manifold, it's a problem because you can't do it. You need to know two things. You need to know the function f that you're interested in, but you also need to know the curve along which you're going to define the derivative, because this is the definition of the derivative. It's the function and the curve, right? With respect to the parameterization of the curve. Lambda is called the parameterization of the curve. If you reparameterize the curve, for example, if I were to reparameterize the curve from lambda to some other independent variable, say kappa, and I said that kappa equals 2 lambda, that's a different curve. It has the exact same points as beta does, but it traverses them more quickly, right? Twice as quickly. So that counts as a different curve. So each parameterization of a curve is a different curve. So the point being that to find these derivatives, I need more than just calculating a derivative. In regular calculus, you didn't need to know anything special because you always had real numbers going to real numbers, and all you needed was, there's only one way to take the derivative of a one-dimensional function, right? If this was a one-dimensional manifold, this wouldn't really be a problem. But because it's more than one dimension, you have to ask, what curve are you interested in finding the derivative of the function? There is no definition of the derivative of a function f at a point P, in other words, right? You can't do that. You can only do that if you know the appropriate curve.
But if you do know the appropriate curve, you've got it. You can do it. You can calculate this value if you know a curve. So that allows us to say, all right, let's think about how to define the derivative of the function f on a manifold at a point. How can we consolidate all this stuff to a single simple notation? So let me erase this, and we'll do that now. So to make this notation, we are going to, I'll go in black now, we take our function f, which we draw from C infinity. We take our curve alpha, which we draw from A, I guess on the manifold. We take those two things, and then we take a point P, which is a member of the manifold. So all of these things, of course, are necessary. And I mean necessary not only in the sense that they're necessary to create this concept of the derivative, but they necessarily exist, which means that this is all automatic. There's nothing that we're doing here that involves any mathematical creativity. So now I want to talk about the derivative of the function f at the point P associated with the curve alpha. And we've already written down one version of how this will look, right? We know that this is going to be df alpha of tau d tau evaluated at alpha inverse of P, right? So every one of these things that we need is in this notation. F alpha, point P, and tau is, of course, this is the parameter of the curve, right? And this could also be written, it's also, what this literally means, I should say, probably, is F after alpha, right? D tau evaluated at alpha inverse of P. Now, this notation here, notice I left off the tau. I could put it in there. I could say as a function of tau. Kind of looks like you're multiplying things, right? So it's a little bit awkward, but this is the name of a function, right? And given that this is the name of the function, if I'm going to be consistent and put the dependent variable in the this expression for the derivative, which we sometimes do, I should put it in there. But look, I could also do this. F after alpha of tau. I could do that too, right? Because this symbol for composition, this composition symbol, that necessarily must bind these together first, right? Because that's what this is the name of a function. So if I understand that as the name of a function, then it's not unambiguous anymore, right? There might be some ambiguity. Am I talking about f after alpha of tau? Well, alpha of tau is a number, so you can't have a function after a number. You have to have a function after a function. The composition operator is expecting two functions, so the only logical way of interpreting this is this after tau, with this grouping after tau. So you don't even need these parentheses here. You could do it this way. So this makes sense. But you could also just drop tau altogether, right? Because it's obvious that this is a function of tau because it's an ordinary derivative and the independent variable is given here. So this function must be a function of tau, right? So I could actually just write it. Let me erase all of this stuff because this is just sort of explanatory stuff and go back to our first notation, and I could write it like that, right? df alpha d tau. There's only one choice for this. So given that this is an unambiguous thing that must exist if I have f alpha and a point P. So instead of writing all this every time, I'm going to give it a simple name. I'm going to call it V, right, of alpha of P, right, and it acts on F, right? That means this, right? That means this. That means the derivative of the function f along the curve alpha with respect to the independent variable that parameterizes the curve evaluated at
the value of the parameter tau that corresponds to the curve going through the point P. Phew. So that's what this thing is. That's what V alpha P means, right? So I could write V alpha P of the function G, and that means, by definition, that's why I have 3 lines there, D G alpha D lambda evaluated at alpha inverse of P, right? And lambda now is the parameter for the curve alpha in this case. Whatever's down here is the parameter of the curve alpha, because you have to take the derivative with respect to a real number, with respect to a real parameter. And that's what this is. So these guys here now, that necessarily exists at the point P, right? This is an operator, right? It's an operator. It acts on F. In fact, you can think of it as a mapping, right? V, let me go back to black here. V alpha P is a map from C infinity to the real numbers, right? You put in a function, and you evaluate this expression, oh, God darn it. You evaluate this expression, right? That expression is a number, right? You determine what this derivative, this derivative is a function, right? This part is a member of C infinity, but you evaluate that at a specific value of the parameter, one that corresponds to the point P. This is a real number. So this guy is actually a map from all differentiable functions on the manifold to the real numbers, right? And the way I create this map is I need a curve and I need a point, right? So this guy here, that's our object of study now, right? All the possible versions of this at a point P would then be replacing alpha with every conceivable curve, right? So in order to understand every conceivable derivative, actually we should give this a name. I'm going to call this the directional derivative. And when I say I'm going to call it, that's absurd. That's what this is called, right? I'm introducing the term, but it's standard language. The directional derivative. This is the directional derivative, I guess you should say, at P along alpha, right? The directional derivative at P along alpha. And the big takeaway, the thing that we've been building up to, is it is necessary in the sense that it necessarily exists. Alpha necessarily exists, P necessarily exists, F, or this C infinity necessarily exists, R necessarily exists, ergo, it is necessary that this guy exists. So we didn't create it, it was created, it came into existence when the manifold came into existence. Now, V alpha didn't actually specifically come into existence all by itself. What did come into existence is the set of all possible V alpha P, right? Because we have the set A, which necessarily exists on the manifold, the set of all possible curves. I should say this is now the set of all possible curves that go through P. So let me put that down. The set A exists, right? The set of all possible curves on M, but then I can take the subset of those curves that just go through P. And that subset necessarily exists. So the set of all possible directional derivatives is all possible derivatives at the point P, right, of all possible curves that go through the point P, right? So this infinite set is yet another uncountably infinite set that definitely exists. And there's one of them for every point on the manifold, right? So that's really critical. That's sort of a big step. That means at the point P, I can establish the set of all directional derivatives, every conceivable directional derivative, and there's one for every curve that goes through P, right? One for every member of AM of A that goes through P, every one of those, there's a one-to-one correspondence to V alpha P, right? It's a one-to-one correspondence. And so for every curve gives you a directional derivative. And this directional derivative is an operator that takes functions on the manifold and returns real numbers. But you must think of these guys not just as their action on these functions. That's what defines them. But they exist independent of these actions. This is a set. This is a set that exists in its own right, right? Even if you don't pull out F. Notice that F is not a part of the definition of V, right? The literal definition of V is something like, it would be something like V alpha of P is literally defined as D with respect to tau evaluated at alpha inverse of P. I guess you would need an after alpha right there, and you have an empty slot for some element of C infinity to go there. So when you put in a C infinity here, say, G or F or whatever, then you get a real number. But without that, you just have an operator. And then you can make the set of all these operators, and that's a thing, right? That just because it's not operating on something doesn't mean it's not a thing. It's a thing unto itself. The analogy I used earlier is a hammer may be a tool that doesn't have much obvious use without nails, but you can still make a collection of hammers. You can put hammers in a toolbox. You can use one hammer and then another hammer right after it. I mean, there's a lot you can do. I mean, hammers are things into themselves, and that's what this is. And ultimately, this mathematical object is what we're going to study. But look what we've got. We've now got a set of something that exists at each point in a manifold, and it's different at every point, right? Like if I take this point here, R, there is a set of V alpha R, right? And that's an uncountably infinite number of operators that act on arbitrary functions that come from C infinity. And if I should feed it a function, it will ultimately give me a real number. It will ultimately give me a real number. And that's true for every single point on the manifold. V alpha, I guess that's Q, right? So at the point Q. Every single point has this set. And ultimately, that is what our tangent space is going to become from. What I'm now going to show you is that each of these sets is not only just a set of all possible directional derivatives that necessarily exist at each point, but I'm going to show you that each of these sets is a vector space in its own right, right? I'm going to prove to you that each set is a vector space, or can be easily understood as a vector space, I guess is the right way to say it. Because a set isn't a vector space. A set is just a set. But when you have a set and you can define addition on the set, and you can define an inverse on the set, and the set is closed under this addition, it's closed under this notion of inverse, and then you can say that there's a zero element in the set, then the set becomes a vector space. So we will define addition in this set, and inverse in this set, and zero on this set, and show that each set can very easily be understood as a vector space. And that vector space will be the tangent space. So that's the next part of this lecture. We've gotten this far. We've found necessarily at every point on this manifold, no matter what manifold you have, if it's a manifold, it must necessarily at every point have this set of directional derivatives. And that leans on the existence of the set of all possible curves that go through the point, and it leans on the fact that every manifold has a set of infinitely differentiable functions from the manifold onto the real line. And now that we have that, I'm now going to prove that this is a vector space. And then after that, I'm going to explain why we call it the tangent space. Okay, so let's finish up.
All right, so now we have our set of all directional derivatives at P. And P is fixed in this story, right? As I'm sure you understand by now. P is fixed. Alpha runs through every member of the set A, P of M, which is every curve that goes through P of M. So if this is the point P in the manifold, our set AP of M is the set of every one of these curves that goes through P. No matter how weird the curve is, it can go anywhere, but it goes through P, right? And usually when we do that, by the way, there's really no loss in setting it so that for every single curve, alpha of 0 actually equals P. So we're going to assume that too, right? That's not a thing. Meaning that doesn't change anything. We retain full generality by assuming that this is true for every curve that is in AP of M, right? So now I want to show that this object can easily be understood as a vector space. As it is now, it's just a set, right? So to understand it as a vector space, I have to show a couple different things. I have to show that, first of all, I have to decide, do I want it to be a real vector space or a complex vector space or the vector space of some arbitrary field, right? And the answer is I'm interested in it being a real vector space, right? So I'm going to show that it's a real vector space. And I'm going so to show that it's a real vector space, I'm presuming that I'm carrying along with this the scalars, right? The scalars of the vector space are going to be the real numbers, right? So that's very important. So what does that mean? That means any member of this set, any directional derivative of this set, I have to be able to take a member of the real numbers, and I have to define scalar multiplication. So if that member is A, I have to know that I can define this thing. I can define A multiplied, scalar multiplied, by a member of the set, a directional derivative, and this thing had better be a directional derivative also, right? The directional derivative of some curve, right? That means that there's another member of the set, V beta P, which equals A V alpha of P. So I have to show that. And I have to show also, let's see, what else do I have to show? I have to show that if I have two members of the set, V alpha P, I can add them together. I can define an addition, V beta of P, and that result has also got to be a member of the set, which means that there's some other curve gamma that can be understood as the addition of two other, that the directional derivative with respect to some identifiable curve gamma, which is also a member of APM, obviously, I should be able to identify a curve gamma that can logically be understood that the directional derivative with respect to this curve gamma is logically related to what I can call to be the sum of the directional derivatives with respect to the curve alpha and the curve beta. It turns out this is easy, this is hard. And when I say hard, I mean this takes like 15 lines of work and a little bit of insight. This one takes insight and 15 lines of work. And this one, I think, is very, very easy. So let's dispense with the easy one first. All right, so we are looking for a logical understanding of the scalar product in our set. And our set that we're dealing with is V alpha P, where alpha is all possible curves. It's this, and so we want to understand is how do we take our real number, which is what A is, how do we take a member of the set, which is what V is, and produce this thing, which is a scalar product. And that scalar product has to be in the set also, right? It's closed under this scalar product. So how do we define the notion of a real number multiplied by a directional derivative? Well, what this has to mean, in order to make any sense, this has to be
some other directional derivative. So there's some other curve, gamma. I better not use gamma because my gammas are going to start leaning over and look like alphas, given how sloppy my writing can be. So let's go with beta at the point P. So there is some curve beta whose directional derivative at the point P has got to be the same as the so-called scalar product of some number A times this other curve P. And for every curve A and any real number A, for every curve alpha and any real number A, I need to be able to define a curve B such that this is a directional derivative. The directional derivative of B is what is equal to what we're going to call the scalar product. So how do we do this? Well, what we're going to do is we're going to lean on the fact that A is an element of the real numbers, and we can multiply two elements of the real numbers. Say I had the number B. I know that A times B equals C, where this multiplication here is just regular real number multiplication. So I'm going to try to lean on that fact to come up with a way of defining this curve B, to know that we are defining this scalar multiplication in such a way that there will always be a curve B whose directional derivative will make sense under that definition. So let's do that. All right, so we're going to start by blowing up this guy, right? And we know that V alpha of P is equal to the derivative with respect to tau of whoops. I guess what I want to say is I need to put my little f there, right? Drawn from the functions of f after, and I think I'll do alpha in blue. Might as well try to do all these things by color. D f out blue d tau, ups, undo, and then I want this part in black. I want, and then I guess alpha inverse of P. Now, implicit in this is the fact that alpha is parameterized by tau. But let's say we change the parameterization of alpha. Let's imagine for a moment that alpha was parameterized by some other parameter, lambda. And lambda is a function of tau. So lambda is a function of tau. So for every value of tau that we had in this old case, we replace it with lambda of tau, and we get alpha as a function of lambda. That's just a simple reparameterization of the curve. Well, if we did that, how would that affect this definition? If now alpha is no longer a function of tau, it's a function of lambda. Well, we apply the chain rule, right? So we apply the chain rule. And the chain rule would make things look like this. So first, blowing this up using the chain rule gives us this expression here. This is basically the derivative of the function f acting on the function alpha of tau multiplied by the derivative of alpha with respect to tau. And it's all then evaluated at the alpha inverse of the point P, which will usually be 0, right? We're setting these functions up, by the way, so that alpha inverse of P equals 0, right? So that's important to understand. But if we change the parameterization to lambda, where remember lambda is a function of tau, then we add this additional piece here, which is the chain rule expansion d lambda d tau. Because remember, the derivative is with respect to tau. So in the end, the final chain rule piece has to have this in it. But it's still evaluated at the same spot, alpha inverse of P. Now alpha is a function of lambda, but again, we've set it all up so that lambda will be 0 at P as well. So I guess this should be black. This line here should be black. Not that it matters much, just to be consistent with this line and this line. So this part here, right, is functionally identical to this, right? It's just this thing that matters. So this evaluates to a real number, right? This evaluates to a real number. So I want this real number to be equal to, I might say, okay, this real number is going to be equal to is going to be related to our scalar product. If I take d lambda d tau to equal a, right, if I take this and I set that equal to a, which is another way of saying that d lambda d tau equals a, so lambda equals a tau plus c, but because I want alpha lambda to equal alpha, I want alpha 0 to equal alpha as a function of lambda at 0 equals alpha as a function of tau at 0 has to equal, wait a minute, hold on. I want alpha lambda equals 0 to equal alpha tau equals 0 to equal p, then the only way that works is if c is 0, right? So we set c equal to 0, which is an arbitrary integration constant. So if I set this guy here to equal a, then this term here would become a, like that. Now, if that equals a, then I know that lambda equals a tau, and therefore alpha of lambda simply equals alpha of a tau. And this is a different curve in our set. So now if I created the directional derivative v of the curve alpha a tau p, this curve here we identify with a times v alpha of tau p. So if so multiplying by a scalar simply reparameterizes the curve itself to be faster or slower, depending on whether a is greater than or less than 1. So I know that the set A at P of M contains every single curve that goes through the point. So it includes the curve alpha of tau, and it also includes the curve beta of tau, which actually, or beta of lambda. Well, let's see. It includes the curve beta of, I guess, lambda, where the definition is beta of lambda equals alpha of a times tau, right? And so I've found my curve that satisfies this property. In other words, I've found a curve such that I can define scalar multiplication such that I've discovered another directional derivative in the set that can be identified with the scalar product of any directional derivative times a real number. Okay? So we now have defined a scalar product, and our set is closed under scalar products. Okay, so that takes care of one of them. Now let's go to that's the easy one, right? Let's go to the hard one. All right, so now let's begin with our manifold and our point P. And let's look at a curve that goes through the point P. And we'll call that curve gamma. And let's look at another curve that goes to the point P, and we'll call that curve, let's call it beta. Right, we're going to call it beta. So we have two curves going through the point B, and therefore we have two directional derivatives that we can talk about that go through this point. And that directional derivative, the first one is V gamma at P, and the other one is V beta at P. So what do I need to do? I'm trying to show that the set of all directional derivatives is a vector space, so I have to define vector addition. I've already got scalar multiplication. I have to define vector addition so that I can take any two vectors, add them together, and find a third vector. So what that is in the set. It has to be closed under this vector addition. So what does this mean? This means I have to be able to derive an expression that looks like V
it looks like this. That is, the curve gamma and the curve beta, those two directional derivatives, when I add them together, I have to come up with a rule that when I add these two together will give me a directional derivative of some other curve, phi, right? Every directional derivative must be defined by a curve. So if these two sum to another directional derivative, there's a curve out there that defines that directional derivative. No curve, no directional derivative. So that other directional derivative, I guess I will, I'll draw in here in, I guess, red. How about red? So there's some other curve that goes through P. It has to go through P, otherwise it wouldn't be at part of the set that I'm trying to turn into a vector space. And I'm going to call that phi. So somehow I've got to define this new curve, not that it's the sum of the other curves, right? It's the sum of their directional derivatives. I have to come up with this. So how are we going to do this? Well, now is one of the places where this idea of blowing up the manifold, this is a chart on the manifold, this is a chart U on the manifold M. So I guess in some sense the whole plane is the manifold and this is just a chart on it. You can always do it. There's the point P, there's a chart on P. These curves are defined on this chart for now. You don't need to worry too much about what the curves do here, by the way. What's really important is what they do right in the vicinity of P. But this chart M exists, as we've talked about, and now we're going to reintroduce the all-important chart mapping X, which takes this manifold and puts us into Rn. Now, previously I've been saying, okay, we're just, you just got to have this mentally established in your mind, and we don't need to explicitly think about it. But now we are going to explicitly think about it. And so the point P inside this Rn, this has coordinates, and that coordinate will be given by x of P. That's the coordinate of the point P. The coordinates, it's x of P, where x is now the chart mapping from M to Rn. So we want to revisit the nature of these curves, and we want to understand the coordinates of the curves. So the coordinates of the curve, we know that gamma, and I guess I'll do it in blue, gamma takes the real line and gives you the manifold, right? Gamma is a map from the real line to the manifold because it's a curve. But we know that x after gamma is from the real line not to the manifold but to Rn. And x after gamma is the coordinates of the points along the curve. So now x after gamma is a function of the parameter of gamma, which I could call, say, tau. But the result is an ordered pair of points, x0, or an order n tuple of points, all the way to xn minus 1, right? That's what this means. So x after gamma is very important. So we're going to reintroduce a chart. Now we know we're not going to specify in any detail what the chart is, but because we're dealing with a manifold, the chart necessarily exists. Again, every step we take here, every single step necessarily exists irrespective of any decision or choice we make. We know this choice can be made in principle every single time. There's always going to be a chart mapping because it's a manifold, and manifolds are defined as things that have coordinates, where coordinates are, in fact, these mappings. It's sort of absurd to say a manifold is something that has coordinates. No, manifold has charts and chart maps, and those are coordinates. Okay, so we're now going to reintroduce this, and we're now going to think about x after gamma. And likewise, we're going to think about x after beta, which is also a mapping from real numbers to Rn, right? And so now these curves are actually, you could almost imagine them living down in here, right? There's the blue curve here, and there's the beta green curve here, and they're in Rn. So we're now thinking again about coordinates. So we've
we've introduced some level of constraint because we have to have a coordinate system in the story. So now let's think about another curve. We're talking about addition here, right? So we can add two curves together because remember, this is a set, this is an n tuple, and this is an n tuple. And we can add n tuples by adding the first tuples together, the second tuples together, or the first element of the tuple together, the second element together, and we get another tuple, right? I guess we could say A, B, C, D plus E, F, G, H. Here's 4 tuples. Well, that equals A plus E, B plus F, C plus G, D plus H. So we can imagine that. That's not hard. That is, by the way, how you would define addition in Rn, right, if you had to. So with that in mind, let's consider the following curve. Let's consider x after gamma plus x after beta. And what would this curve be? Well, consider its value at the point P. The value of this curve at the point P would be the n tuple derived at the point P from this plus the n tuple derived at the point P from that. Well, let's say the point P has coordinates, well, we know what it has, right? It has coordinates x of P. So that, say those values are x0 of P, x1 of P, dot, 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 to xn minus 1 of P, right? This sum evaluated at gamma inverse of P, which would be the same as beta inverse of P, right? Because we always set these curves up so that beta of 0 equals gamma of 0, which will equal P, right? We're setting it up so that the parameterized, however these curves are parameterized, the 0 values at P, right? So if that's the case, then this is the coordinates of the point P, and this is the coordinates of the point P. And therefore, the sum of those is going to just be twice, it's going to be basically 2 times the coordinates of point P. So at the parameter value equal to 0, this curve, which I'll call this curve phi, at the parameter value 0, phi is not going to be at P. Phi is going to be at some other point, say here. And that point is going to have, the coordinates of that point is going to be 2 times x of P. Right? So it's going to be somewhere else. And in fact, at the parameter value, if every curve in our story, meaning every curve in AP of M, has to be such that the curve at 0 equals P, which we're allowed to do, right? That's not, that we can do that in full generality. The point is that this curve, phi, would not satisfy this. This curve would not be a curve parameterized such that its 0 value would be at P. So this curve's no good. This curve's not really in this set. So just adding the coordinates of the curves together to create the coordinates of a new curve isn't going to work. And actually, I shouldn't write psi there, right? I should write x after psi. So, but this does tell us, well, wait a minute, how can I make this work? Well, you can actually make this work without too much trouble by defining psi only slightly differently. In fact, this gives us a big hint about what to do. Now I'll do everything in black here. If I take a curve whose coordinates, I take a curve psi, the coordinates of psi I'm now going to define as the coordinates of gamma plus the coordinates of beta minus the coordinates of the point P, right? And understand, this is completely plausible. This is the coordinates of a point on the curve. This is the coordinates of the point on the beta curve. And this is just the coordinates of a point. This basically is effectively subtracting off a constant. And if I did that, we know that this is 2 times the coordinate. So if I subtract this, it actually puts it back at P, right? So I'm going to propose that this definition for psi will work such that this vector addition is logical. In other words, I'm looking for a curve psi that can logically form a directional derivative that can logically be considered to be the sum of the directional derivatives of 2 given curves, gamma and beta. Well, I'm going to propose that if I want to find this psi, the coordinates of psi are going to be the coordinates of gamma plus the coordinates of beta minus the coordinates of the point P, which is part of our definition. So we have access to this point. This whole story happens at P, and P has coordinates, so I can subtract those coordinates off. So I want to define psi to be this curve, and now I want to study the directional derivative of this curve and see if I can get a rule that means the directional derivative of this curve when applied to f is equal to the sum of the 2 real numbers I get when I apply the directional derivatives of gamma and beta applied to f. Because remember, this is a real number, that's a real number, and that's a real number. So this is real number addition, right? That's real number addition the way I've written it. As soon as I put a test function in there, I can use real number addition to broker the notion of vector addition, which is this, right? So the question is, is this good enough? Is this the curve that I'm looking for, right? So now we are going to prove, yes, that is the curve we are looking for. This is going to be a proof by demonstration, right? Instead of finding the curve psi, I'm going to demonstrate that, hey, somebody handed me this thing, and it is psi. So I've proven that this thing works, that this definition of addition is closed, not by finding psi, but by taking a psi that's been given and proving that it satisfies it, right? It's sort of, I'm demonstrating that this satisfies the rule. Now, how we got this has to do with like the history of mathematics, but I just kind of showed you, we kind of did a little plausible thing here, you know, getting this coordinate to come back here. This is something worth trying. Let's see if this works. If it does work, we're done. If it doesn't work, then we've got to do more math. Turns out it will work. All right, so let's take the directional derivative of this and show that it equals the sum of these 2 directional derivatives. All right, so we begin with our proposed definition of this so-called sum curve, the curve of the curve whose directional derivative is going to equal the sum of the directional derivatives. Like this. This is the idea. So now let's insert the definition of the directional derivative that we're going to use right here. Okay, so here it is. This is the definition of that, right? That's how we define it. This is the derivative with respect to the parameter of the curve psi. So that's just a straight definition of this directional derivative at p of phi, not psi, phi. But I'm going to write this a little bit differently. In the previous lectures where I discussed this, I used this other notation, but it's going to be f after phi prime, where prime is basically this, right? You're always taking the derivative with respect to the curve's parameter, right? But it's still evaluated at phi inverse of p, right? So now I've converted the left-hand side to this notation here. So now notice that this does not have any of the chart stuff in it, right? The chart stuff in it lives up here in the way we define this curve, but it's not It's not in this definition. So we need to insert the chart stuff. So how do we insert the chart stuff? Well, we just remember that x inverse after x equals the identity. So we can always stick in the identity. So that's what we're going to do. So this is totally allowed, right? This is sort of the identity right there, right? So we've done nothing, but in some sense we actually have done something because we've introduced a chart. So right now, whatever we prove from this point on is going to depend on the chart we use. So all of a sudden, everything now is coordinate dependent. If I'm going to make this move and put in x, it's coordinate dependent. Now, right now in this form, I can immediately eliminate x and get back to here, which is coordinate independent. There's no charts at all in this, right? I literally can remember how I said, oh, when you think of f, you think of it as a function from Rn to R, because even though f is defined on the manifold and really takes points in the manifold, you're actually thinking of x after f, right? So it's, or I'm sorry, I guess it's f after x inverse, right? And that's Rn to R. Well, now we don't have to do that. Now we're being literal. F is literally from the manifold to the real numbers, and this is from the real numbers into the manifold. Now we are literally talking about the coordinates of the curve, right? This is the coordinates of the curve being fed back into the manifold, and then f is applied to it to give us a real number, right? But now we have charts involved, so we got to be aware that now we have broken the chart independent or the coordinate independent nature of things. Even though it's kind of trivial, and it's still evidently coordinate independent because we know these two things cancel, but as we proceed, we got to make sure we keep track of this point. All right, so the next thing we're going to do is we're now going to apply the chain rule. We're going to think of this as one function and another function, right? So there's two functions. So this is now, if I call that function, say, A, and that function B, this is now A after B. So we have something of the structure A after B prime, which is really A of B prime, which is going to be A prime times B prime, right? It's the chain rule, right? It's going to be the chain rule. This is a sort of a quick and dirty description of how the chain rule works, but we're going to now apply the chain rule to this object here that we've divided up f after x inverse after x after psi. So the structure of that is going to be the derivative of this of the combined function. I shouldn't say combined. What do I mean? I mean the derivative of this composition, right? You're composing this with this. You're executing this first and then that. So the derivative of a composition using the chain rule is going to be the derivative of this times the derivative of this. But remember, we're evaluating it at phi inverse of p. So how does that apply to these functions? Because the domains are not quite right. Well, this one's fine, right? This one will be evaluated at phi inverse of p. This guy, it's a little bit trickier because basically you have to go from, you have to look at this function, right? X inverse takes a point in Rn and gives you a point in the manifold, and f takes a point in the manifold and gives you a real number. So if I'm evaluating it at phi inverse of p, that's a point on the real line in the domain of the curve. So I have to go from the domain of the curve, which is phi inverse of p. I have to take it back into the manifold, which is phi of phi inverse of p. But ultimately, I need a coordinate to be acted on by the x inverse. So then I need to go x after. So the chain rule complicates it, because when you split the chain rule up, the domain of this guy is different than the domain of that guy. So this now is the expression. And now it's a little less obvious, right, that the coordinate chart cancels out. I mean, the point is this and this are in fact identical. So we do know that the coordinate chart's still going to cancel out. In fact, that happens throughout this entire process. But it's not quite as obvious anymore. But we have to remember that in the end, whatever we land with better not have any coordinate charts. Otherwise, the answer is going to be coordinate dependent. Okay, so now we have this, and that was because of the chain rule. So what's our next step? Well, one thing we can do is we can take this stuff and just do the obvious, right? This and this invert each other, right? And the inversion is just, well, let's see, you start with a point P in the manifold, you go to the real line, you come from the real line, you end up back in the manifold. So now you have x operating on this is just x operating on P. And x, of course, is a map from the manifold to Rn. So this whole thing really is just x of P, right? It's just the chart mapping of the point P. It's the coordinates of the point P. That's what this is. So, which is, of course, the way we designed it. So let's just simplify that and write it in its simpler form, x of P. Okay, so now what's nice is that our test function is over here, and now is the time to apply our theory. Our theory is that this is, in fact, how you define psi. Let's see, how do I say it? We have x after phi here, and x after phi is sort of how we're defining phi. So now I can substitute this for x after phi. And this is a theory, right? This is a hypothesis that this is a good choice, right? That if I do make this substitution, I'm ultimately going to end up with this, right? So let's try it. Let's make that substitution right now. Let's see, I guess I got to go back down here. I'm going to run out of room. So I guess this is the substitution, right? This piece becomes that, and everything else is the same. I changed the color of this for some reason. I guess it should all be black at this point. There's really no benefit using colors. So now I have this derivative. So derivatives, remember, these derivatives, by the way, are always derivatives with respect to the derivatives are always derivatives with respect to the parameter. So whatever the parameter is, we're going to maybe assume everything is parameterized with the same parameter, which again, no loss of generality to assume that. So this derivative, obviously, the derivative process is linear. So the derivative of the sum of three things, or the sum of two things and the difference of one thing, is going to equal the derivative of the things. So that's our obvious next step, where the derivative of this guy is 0 because that's a constant. So let's see if I'll copy this to another screen and then do it. So I'll just write this one out along with you. So I'm going to write x after gamma prime evaluated at phi inverse of p times f after x inverse prime evaluated at x of p. Right, so that's the derivative of the first term times this thing. Remember, this thing's just a number, right? It's the derivative of this expression evaluated at this. It's all linear, right? Even if it wasn't a number, even if it was a function, we're talking about the linearity of this derivative over that, and that's being multiplied by this whole thing. So this is the first term of that, and then a very similar second term. All right. So this is this is the second version of this, and this is a constant, right? This is a constant, so its derivative is 0. So there's no third term. So this is the next step, right? And you can see where this is going, right? This guy here looks a lot like the definition of the derivative, directional derivative of the curve gamma, and this looks like the directional derivative of the curve beta, right? So that's kind of interesting, and that's sort of what we're after. Remember, what we're actually after here is this expression. So this guy and this guy are just popped out, are just beginning to pop up. So let's keep going. Now remember, we agreed that all the points, at the point P, all the curves, for example, gamma, beta, and by construction, phi, we all have it so that the zero value of the parameter equals the point P. So it is true that phi inverse of the point P, right, equals gamma inverse of the point P equals beta inverse of the point P. So, which means that if I'm standing at the point P and I pull out the parameter value of the phi curve, that parameter value is going to be the same as the parameter value for the gamma curve and the beta curve. We've done that by construction, right? We're assuming that all these curves are parameterized such that at the point P, all the curves have the same parameter value. Now, off the point P, they're all totally different, but at the point P, they all have the same parameter value. That allows me to change this and this, right, using this to gamma inverse at P and beta inverse at P, which is what I kind of need. So let me do that. I guess I would just do it by erasing this, and I'll write it here in red. I'll write this is gamma inverse at P, and I'll erase this, and I'll write this is beta inverse at P, right? Well, that's important because now it really is beginning to look like the velocity function, right? The velocity, remember the directional derivative, the directional derivative at the point P along the direction gamma involves this derivative with respect to the parameter evaluated at the inverse of that same curve at P. So now I've got that in both of these spots. So this literally does match the definition of directional derivative now. But notice carefully the structure of, well, first of all, the structure of both of these are identical, right? The structure of this term and the sum and this are the same. It's x after a curve prime evaluated at the inverse of the curve at P multiplied by f after x inverse prime. So this piece and this piece are identical, and these pieces are structurally identical. But if you look at that, this structure here is exactly what we had here, right, for phi, for phi, after applying the chain rule to this object. So we can actually have gone the opposite way. We could have started with this and realized, oh, this is just the chain rule applied to this. And we can do that here. We can invert these two chain rule processes and combine these together utilizing the chain rule, like so. I'll do it off screen. And here you have it. This is an identity, right? There's no substitutions, there's no maneuvering, it's just reversing the chain rule on these two terms to get this and this. And the reason that's important is because now the charts cancel out again, right? X inverse after X is the identity, and what's left is just this and this and this, which is, by definition, this literally is the definition of V gamma P acting on F plus V beta P acting on F. And the whole thing started by being V with our presumed psi or phi at P acting on F, right? So now we're using real number addition on the left to equal a real number on the right, but f is totally arbitrary, so now we define our vector addition this way. And we have proven that if you're given a gamma, any gamma, and you're given a beta, any beta, which means any two curves in AP of M, which means all the possible curves on the manifold that go through the point P that are parameterized such that the curve value at 0 is P. Given any of those two curves, we can find a third curve whose directional derivative is logically understood to be the vector sum of two other directional derivatives. All right, so where do we stand? We stand where we've got our manifold, we've got our points on the manifold, we've got our coordinate system. Presumably there's some chart here that we're dealing with. And now we know that at every single point, we actually can define a vector space that's all those directional derivatives at each point, right? So now this makes total sense. And it's not, when I say we can define, no, it's not that we can define it. It exists. It is absolutely present just because the manifold is a thing that the manifold is, right? This is a mathematical necessity that at every point we can create this thing. And it's a vector space, right? I've only demonstrated that it's got a scalar multiplication and that it's got an addition. But obviously, the zero curve, right? If the curve alpha tau equals 0 was involved, then the directional derivative will be 0 as well, right? So it has an identity element, and v of 0 at p you can show quite easily v of 0 of p plus v of beta of p equals v of beta of p, right? So there's the identity rule works. There's an inverse. You can always define a curve that's the inverse. I won't go through all of those because I think by now you probably could do it yourself, right? If you had to. But every curve will have its inverse curve. And, well, every directional derivative defined by a certain curve, there's another curve out there that'll define a directional derivative that'll be exactly the opposite. And when you add those two directional derivatives together, you're going to get the zero directional derivative, right? So these are vector spaces, right? These are vector spaces. The dimensionality of the vector space is equal to the dimensionality of the curves, which is the same as the dimensionality of the manifold. Curves are in principle one-dimensional, right? Alpha of tau, that's a one-dimensional object. But the coordinates of this thing, right? Alpha, so I guess x after alpha of tau, this goes into Rn, right? So the vector, so these spaces are going to be the same dimensionality as the manifold. Actually, we're going to turn to that question now. So if that's not totally obvious to you, it should be by the end of the next segment. This is a long lecture, but we're nailing down this topic because it's so important and people struggle with it so much. I haven't called these things tangent spaces yet, but ultimately that's what these things are going to be, tangent spaces. Okay, so what is the next issue we have to get to understand well, we've got vector spaces, right? So now let's find a basis for these vector spaces. That's our next plan. All right, so let me move our big picture over here to the corner, and now we're going to extract this material right here, this thing where we took the definition of the directional derivative of a curve and we blew it up with the chain rule. So I'm going to rewrite this thing as the start of our next analysis. So here it is. I think I reversed the order of the product, but it doesn't matter. I mean, I want to express this guy in terms of its extension. We inserted x inverse after x right in the middle, and then we blew it up with the chain rule, and we end up here. We've done that a couple times already. We did it, for example, we inverted it here, right? We inverted that process here, and we actually did it explicitly here. And this is the phrase I just wrote down in terms of alpha with this term on this side and this term on that side. So it's nothing different. But we're going to look at this thing, and we're going to kind of study it. So this is This is f in terms of coordinates, right? x0, x1 to xn. Now, f in terms of points on the manifold would be written like that. These two things are actually unambiguously different in the sense that the argument list itself tells you that this f represents the function on the manifold and this f represents the same function in terms of its coordinates. Ergo, this is actually x, oops, this is actually, I keep doing this wrong, f after x inverse, right? I don't need to write f after x inverse here if I have the argument list, because the letter f becomes an overloaded operator in the language of computer science, right? So this here is f after f inverse, and I'm going to give this thing a name. I'm going to call this capital F, right? So this is sort of capital F is what I'm doing. And I'm going to give this other thing a name too, right? This guy is the coordinates of the curve, right? So the curve is alpha of tau, but then I'm doing x after alpha of tau. So what I'm getting here is I'm getting n different coordinate functions, right? So I get xi after alpha of tau all the way, et cetera, right? So this is the coordinates of, this would be the each coordinate function of alpha of tau, but I'm kind of talking about them all at once. And that's fine because all at once, for example, this guy would yield me a tuple, an n tuple, right? All the way to xn minus 1. And this guy here gives me a real number, right? Because this is a coordinate of a point P. This takes a coordinate, returns a real number. So this gives me a real number times a tuple. So I end up with a real number times a tuple. And that's what, the directional derivative of P acting on F should be a real number times a tuple. In normal calculus, it would be a vector, right? Which has to have n components. So I'm going to call this guy F, and I'm going to call the other guy, I don't know. Hold on, let me think what to call it. I'll call it H. How about that? H. So I can rewrite this expression. First, I blow this up by adding the x inverse x as before, right? Before I did the chain rule. And then I simply replace it with f after h prime evaluated at alpha inverse of p, right? So all I'm doing is now I have written symbols for the function f in terms of a coordinate and the coordinates of the curve given by alpha. So alpha is a curve in the manifold, and now I'm looking at the expression of a function from the real numbers, the domain of the curve that's in the manifold, the coordinates of that curve in Rn, right? So this are literally identical because I've defined f to be this. I'm not defining f to be the derivative. Defining f to be what's inside the parentheses. I guess that's what I'm trying to get at. All right, so now to understand how to work with this, we need to remind ourselves about the multivariable chain rule. So let me quickly review that. So we presume we have, all right, so the next step involves a piece of multivariable calculus that is easy to not really remember very well. But it has to do with the multivariable chain rule. We're kind of in a place we've already been before, but we're going to do something different now. We're going to break this guy up in a different way. And so we're going to do the multivariable chain rule on this. So let's quickly have a look at the multivariable chain rule. Consider a function, I'll say f, just since we're using f, of h of G, of S, and of R, where H, G, S, and R are themselves functions of t. So we have H of t, G of t, S of t, and R of t, right? So we imagine that circumstance, and we want to find the derivative of f with respect to t. And t is one variable, and this really is, f is really a function of one variable. If each of the, even though it's actually a function of four variables in principle, we've bound all these variables together with a single variable t. So f, as described here, is a function of t. But it's really, f by its core nature is a function of four variables. Anyway, the definition of the chain rule for this circumstance looks like this. So this is that definition. The derivative of f with respect to t, and you can use ordinary derivative here because we're treating f ultimately as a function of one variable. But f by nature is a function of four variables. So this partial derivative of f with respect to h makes perfect sense. And then h, of course, is only a function of one variable, so that's an ordinary derivative. And then you just add all these guys up together, right? So that's how this is done. Now, how does this jive with f composed with h? Well, it looks like f composed with h, where h is a function, h is now a function just of t, right? So that is f of h of t. Now, in this case, t is really, well, let's call it, instead of saying t, let's go back to tau, because tau is the parameter we've been using for these curves, and that's really what h is. But remember, this looks like a function of one variable. F is a function of just one thing, h of t. But what we have to remember is that h is defined as the coordinates of the curve. And this guy x, remember I kept telling you, is actually x0, x1, x2, ... So this is actually f of h0 of t, h1 of t, ... hn minus 1 of t, right? This is all shorthand, right? We're kind of blowing up the shorthand. So this notation and this notation are all the same. So now we apply this multivariable chain rule, and we're going to be taking the derivative of f, the partial derivatives, with respect to each of these slots, and then we're going to multiply by the ordinary derivative of each of the slots with respect to t. But now my simplification of putting h in there, I kind of want to bring that back to the x's, because h is really all these n functions, right? The n coordinate functions. So this guy here is actually f of x0, x1, x2 to xn minus 1, right? These are coordinates, right? Because remember, this is the coordinates of this curve alpha. So ultimately this is the coordinates of a line as a function of tau, right? So all these are functions of tau. I'm writing them in as functions of tau. So now I can write this as, if I want to write the derivative of f h prime dt, now I can apply the chain rule, and I can write the partial derivative of f with respect to x0 times the full derivative of x0 with respect to tau, plus the partial derivative of f
with respect to x1 times the ordinary, I said full derivative, there's no such thing as a full derivative, tau dot 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 partial derivative of f with respect to x n minus 1 dx n minus 1 d tau, right? You add them all together. And I'm going to write this as just the sum of the partial derivative with respect to the ith coordinate of f evaluated at, where's that evaluated at? Well, it's evaluated at the coordinates of the point P, and that each of those terms of the sum is multiplied by hi, the ith piece of h, which is a coordinate, right? Because it's the coordinate of the curve. So it's the ith piece of h. Piece, it's not a piece, it's a, but it's the derivative of the ith piece of h. It's a component. The derivative of the ith component of h evaluated at, what curve am I calling this? Alpha, right? Alpha inverse of p. And this is the multivariable chain rule run in reverse. It's actually sort of it's not a hard thing to do. It's just, you got to remember, we know a lot about multivariable calculus, but the multivariable chain rule we kind of forget. So this one requires a little bit of memory, going back down memory lane of calculus, I guess 3, right? Calc 3 was multivariable calculus, right? Or at least the way I took it, it was Calc 3. So this is the multivariable chain rule where you're summing over I, right? The sum, by the way, you'll notice that I have a lower index and an upper index, implying an Einstein sum kind of thing. But notice this is inside the derivative, really. So we're just going to explicitly write the sum over I. And this derivative here is with respect to tau, right? It's the derivative, the prime, is with respect to the tau. It's the only variable around. H is a function of tau, so or each component of H is a function of tau. So the awkward part here is understanding that when I write x after alpha, that's really a multi-component object. I called it H. I probably could have introduced the I right here to say that's for each of those. Well, no, because it has to be in full generality right there, right? Because we need the output of this object to be a to be an n-tuple. So I don't think I could have put the I in there. But down here in the multivariable calculus thing, you have to put the I in, right? Because you can't define this thing unless you look at each of the slots of F, which is what this I really represents. Anyway, you end up with this guy. And this guy is really important for two reasons. One, if you look at the definition of F, you'll see that the way we defined F, it's in terms of the chart and it's in terms of F, but it's not involving the curve. The curve alpha is all in H, and H is simply a factor, ultimately, that multiplies this guy, right? So this is going to evaluate to a number, and this will also evaluate to a number, so everything should evaluate to a number. But we've separated it into the part where the curve is all over here, and F is all over here. Okay, so I've rewritten it up here. So this is V alpha of P. So let me return F and HI to its rightful kind of description. And that's what this is, right? So here I've just replaced F and H. Where's my I over here? Hold on a second. This needs to be XI. It's the ith. Now I'm because I'm introducing the sum, I've got to keep this I component here, and so I'm referring to the ith coordinate function. So it's alpha. It's the ith coordinate function after alpha, right?
And this is the part I said is dependent only on the function, and this is the part that's dependent on the curve. So now, this part we want to talk about, right? Because here you're starting to see this is the basis vector, right? This is the coordinate basis vector that's going to pop out here. And notice it's actually two parts. This thing is, the coordinate basis vector is going to be this partial derivative operator, and also this instruction to evaluate it at the coordinates of the point P. That's another part of it. It's a two-part thing. It's the basis vector and the instruction to evaluate it at P. So now let's explore what this is and see how much we can learn from it. Well, let's first define it, right? Let's define the following operator. Let's define this object, partial I, at xp. That's going to be defined as, well, it's a map, right? So let me do it this way. It's a map that goes from the C infinity functions on M, right? Of course, that's where F comes from, right? F is a member of this set, and it gives you a real number. But that's the map. So I want to define a map with this name, right? It looks like this name. And the name is very telling because the name is actually a process, and it's an instruction to take the derivative with respect to the ith coordinate function, right? Because this guy here really represents the partial derivative with respect to the ith coordinate, right? So it's a instruction to take that derivative, and it's instruction to evaluate it at this point. But I'm considering it a map from the infinite functions on the manifold to R. So I have to define the map itself a little bit differently, right? Because this guy here, as we see, it's actually operating on a function of Rn, because we have this x inverse in here first. So I'm going to define this mapping as actually by this mapping applied to a function from C infinity, right? You take a function out of C infinity, f, you're actually going to define it as, oops, I lost my parentheses there, as it operating not on f, but on f x inverse, right? You're going to throw in that coordinate. And you can always do it, because remember, this is defined in terms of coordinates. This is the derivative with respect to a coordinate. So you always have x inverse. So the definition of this operator, when it's acting on a function from the manifold, is to first convert the function from the manifold to a function on Rn by just throwing in this x inverse, and then taking its partial derivative with respect to the ith coordinate, and then evaluating the resulting function at the coordinates of the point P, right? That's what the definition of this operator is. And so now I go back up here and I just sort of look at this thing. And because I have my new definition, I simplify things a little bit to clean up these x minuses, as you'll see in a second. This guy is just a number that depends on whatever curve I choose. So this thing was v alpha p, as I've said. So now I can write v alpha of p is actually equal to the sum from I equals, 0 to n minus 1 of partial I, this instruction, evaluated at the coordinates of the point P, operating on, well, this function, let me do it this way. This function operating on a function f from C infinity is this guy operating on f, right, times what I'm going to call vi, where vi is just all of this stuff, right? And this here will evaluate to a number, because this evaluates to a number. This is a number. We sum from all of these things up, so we're just adding numbers, and so we get a number. And now I can actually erase the f, right? I can erase the f and erase the F and put the V on the other side, right? So the V goes here, VI. And now I get the sum of I equals 0 to n minus 1 of VI partial I evaluated at x of p. And so now what I finally discovered is that every directional derivative that lives in this vector space that's at the point P, every one of those directional derivatives, once I choose a chart, right? Notice this is no longer chart independent, right? Once I choose a chart, I can always write that directional derivative as some number times this operator, right? As some number times these operators. And there's going to be n of these operators. There's going to be n of them. And they actually, every single curve, this VI is well defined. And it's well defined by this process right here. That's unambiguous. It's absolutely clear. If I have an alpha and I have a manifold, if I have an alpha, I have a curve. If I have a manifold, I have a coordinate system. And if it's a curve, it's invertible. So this always exists. So every directional derivative inside this space can always be written in this form. And now it's very easy to break this up. Let me go back to black. This equals the sum from I equals 0 to n minus 1. And it's VI partial I, where I'll now suppress this part just because it's understood that we're dealing with the tangent space at a point, so it's always going to be evaluated at that point. And now we're into the notation. Now this ultimately becomes VI partial I, which is what we use for our vector spaces on the manifold. And this is actually the basis, right? These operators are the basis vectors. This is a real number, right? That's a real number. So that's just a member of the scalars of the vector space, right? So this process, this multiplication of VI times partial I is scalar multiplication. This guy is the basis vector that we're going to use, and it's an operator, right? And it completely spans this space. I'm not going to prove that it spans the space. I guess what I have to do, well, it spans the space by construction, but there is some question, are they linearly independent? Or, can you add some combination, linear combination of these partials together to get one of the other partials? And the answer is no, you can't. They are linearly independent and they span the space. And this basis, it's dependent on the coordinate system, right? Without the coordinate system, you couldn't do this. You can't define these functions. You can't define any of this without a coordinate system. And its remnant is here because this represents the partial derivative with respect to the ith coordinate. If you don't have a coordinate system, you don't have the ith coordinate. So this part is coordinate dependent. And if you change your basis, right? If you change the coordinate system, right? Remember, if you change the coordinate system on the manifold, then you change the nature of these derivatives. So when we say it's coordinate dependent, it's dependent on the coordinates on the manifold, and the basis, these operators change because you're changing the variables by which you're differentiating if you change the underlying coordinate system. So changing the coordinate system on the manifold will change the basis within each and every single vector space defined on the manifold. All right, so good enough. Now, where do we stand? Well, we started with our manifold. We identified the coordinate system on the manifold, which I guess we called X. And then at each point, we realized, hey, we know that we have the set of all functions on the manifold. We know we have the set of all curves on the manifold. We know we have the set of all curves that go through these points on the manifold for which are parameterized such that the 0 point is the point. That's easy to do. And because these are automatic, it turns out that it's also automatic that we have the set of all directional derivatives of every single point on the manifold. And now we know that once we have this coordinate system x, we also have this basis. These are real numbers. We have this basis of operators that exist on this manifold exist in each of these tangent spaces. And this applies to, what's beautiful about this, of course, is that it applies to every single point. This is point Q, right? So not P anymore, but it's Q. It's Q, 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 Q. And the thing that makes this different here and here is the instruction that follows these partial derivatives. And this is another confusing thing. There's an instruction here that is left off because it's just so unwieldy, and that is evaluated at the point P. And likewise, there's an instruction here for this partial derivative. These partial derivatives that are the basis vectors are evaluated at the coordinates of the point Q. And that instruction is what distinguishes these tangent spaces a lot. I mean, otherwise it's just the derivative with respect to a variable of a function, and that's not going to be different. But it's the evaluation of that at the coordinates of the point that supports the vector space that makes these things different. So it is a little confusing to say, oh, that's the coordinate basis. What it is that's the coordinate basis at the coordinates of the point P, right? And this is the coordinate basis at the point P, which is just not the same as partial I evaluated at the coordinates of the point Q, right? So every tangent space, its basis is uniquely attached to the manifold at a point through this part of the instruction, which is almost always suppressed. We never write that instruction down, so you never see it. And that's one of the things I think that confuses a lot of students about this. All right, so now that's where we stand. We have created the vector space everywhere, and basically we're done. This is like a 2.5-hour lecture or something. The only thing left to do is the set that I've been calling directional derivatives at B of Q, right? That now has to be understood as just the tangent space at the point P for the manifold M. And, we no longer think about curves anymore, right? Because the curves are we've learned that the part that's related to the curves just evaluates ultimately to a real number. So all we have to do now is think about the tangent space of each of these, the tangent space at the point P of M instead of the directional derivative. We say it's a real vector space. The basis vectors are partial I, and why don't we just go for evaluated xp? Let's just be real complete about it, right? And every vector can be written as vi partial I, where vi is a real number, right? That's all you need. You no longer, all the stories about curves just kind of goes away, right? Because vector spaces are so simple, right? That we always know, let's put it this way. We always know that if I pick any real numbers, a partial 0 plus b partial 1 plus plus say c partial 2, right? So I've got v I partial I, where I'm suppressing the instruction to evaluate it at the point P, right? I'm suppressing that instruction right now. But say I pick any numbers a, b, and c. Well, I can always find a curve alpha that will yield to me these numbers when I evaluate this expression, right? So the curves don't matter. I just pick real numbers, and there's a curve out there that's going to do it. So we don't have to think about curves anymore. So now everything is going to be understood as a tangent space, right? As a tangent space. We're going to call it the tangent space, T_P of M. Don't worry about the word tangent, by the way, right? Now you understand this is a vector space. I mean, these directional derivatives and all these derivatives are tangencies to the curve, right? So there's totally legitimate reason to call it a tangent space, but don't get wrapped up around that. That's not a reason to be concerned. But we know that all these vector components are real numbers. All of the basis vectors are these operators that we defined very specifically right here, right? That's the definition of the way these operators work. The functions that they operate on are functions on the manifold, not functions on Rn. They're functions on the manifold, but the definition of the derivative immediately converts them to functions on Rn. So, again, it's not a meaningful distinction between these two things, but this is the definition, strictly speaking, how the definition works. So now that we have the tangent spaces on R, the last step is the cotangent spaces on R. But that's the easiest step of all, because the cotangent is nothing more than the map that the dual space is a set space of maps that take vectors in the tangent space, and yield real numbers. So the dual basis to this basis is just some map that takes phi I, evaluated at x of p, which is an operator. Somehow I take that thing and I need a mapping that maps that to the real number 1. And this is, of all the most trivial things in the world, I'm just going to call that map dxi, right? I just name it. I've named it dxi. Don't worry about it being a differential or looking like a differential or being the exterior derivative of the coordinate function or anything like that. Just think of dxi as the map that takes these basis vectors and returns 1. Simple as that. There should be, I guess, technically speaking, some indication on this of what point it's at. But again, we usually suppress all of this. It's all assumed to be in the tangent space located at a point P. Okay, so that is my final effort to try to make the story of the coordinate basis logical and complete to all of the students who've had a big problem. This has been a long lecture, my longest ever, but I'm just going to leave it as one lecture just to be addressed by the students who have trouble with this. Okay, good luck, and we'll talk to you soon.